Swayam Prabha. Digital India. Educated India.
Okay, so I just wanted to finish up. We're going to talk a little more detail about life cycle inventory, creating the input for the life cycle inventory. And then there's also the output of the life cycle inventory that we won't do today. But we will start talking about how do you think about just actually the materials and the amount of materials that go in, with just a few very simple examples. So that was my goal today. And so this is the start of trying to quantify those inputs. And some of you this morning said, oh, but I don't know the amount. Well, that's okay to not know the amount when we do the life cycle thinking, the schematic. But the next step after that is to really think about the input. So where do you find the values for life cycle inventory? The best way to do it is if you have a manufacturing process, if somebody's actually doing it, you go and you get data from them. That is the most accurate, but often the least available information, especially if you're trying to do something for a new product and it hasn't been manufactured yet. Then you really have to think about, I'm not going to get real data, how I'm going to come up with other data. Process flow models like Aspen, which is often used. Has anybody used Aspen? I don't know what you might use. That it's got different sort of reactor types and flows and energy systems. So it's just a modeling tool to help you put together the mass and energy flows for what you assume is going to be, or your best assumption. So that's where a lot of engineering, right? That's where the technical engineering of a chemical engineer or a mechanical engineer might come into play. If it's water treatment, an environmental engineer, that would come into like modeling the system as an engineering. There's a lot of literature that you can search for, industry reports, government reports, literature, other people who have done life cycle assessment, that there's information in those sorts of resources. And if you find things from other literature or from life cycle inventory databases, you got to be careful because they get less and less relevant and specific to what you actually want. You might get good numbers. Say, oh, look at all these numbers, but they might not be for the exact same process that you're doing. So in any of these, there are inaccuracies and limitations. So it's really important to get numbers, but recognize these numbers are not, you don't have 7 significant figures in these, right? Accuracy in these numbers. You might get 2 significant figures worth of accuracy in these numbers, but it's still better than nothing. So you've got to really think about the relevance and the accuracy and the limitations of any data that you might get. So we're just going to do a quick numerical example here to show you sort of some of the things that you might get. And so this is a very rough example just for sort of classroom. So thinking about an automobile. So it's a 1,200 kilogram automobile, 2/3 of steel, 1/3 of polypropylene. And of course, there's lots of other materials in an automobile as well, but this is the majority, right? It's not everything, the battery's not here, but it's a good start. It can drive 200,000 kilometers, consumes 8 liters of gasoline per 100 kilometers. Tires have to be changed, headlight lamp bulbs have to be changed, and so the start would be draw some sort of a system diagram like we did this morning, but simpler. And this time we're going to try to use these numbers to put numbers on that schematic. So this is the information that was given. The car body, we know steel, polypropylene, tires made out of rubber. See, we're missing a lot of stuff here, right? You can imagine, but just for this example. And then there's some assumptions about what goes to a landfill and what can be recycled. And you've got gasoline coming in here. So in this case, we defined the functional unit as driving 1,000 kilometers. Doesn't say anything about people, but it's just driving 1,000 kilometers. And so now our goal is to put numbers on all of these boxes, right? Each of these boxes, so tires, it's really tire manufacturer, headlight manufacturer. So even though it looks like that these are all the processes of making each one of these, so that they are processes in the boxes. So let's see, so what do we have? Our functional unit is 1,000 kilometers. The car can go 200,000 kilometers per car, so it's about 0.005's worth of an automobile, right? It's not the whole automobile gets allocated here, just 0.5%, because we have many years of operations or many miles. So tires, this is just, I like taking care of units. We want to get how many tires, so we know how often they're changed, 50,000 kilometers, and that there are 4 tires for each change. So if you look at the red, so we've got 4 tires per tire change times 50,000 kilometers per tire change. Those are divided, so the tire changes in red cancel out. The kilometers in blue, they cancel out, so we've got our functional unit in there. And then you end up with 0.08 tires worth of material for the functional unit. And then we do the same thing with the headlights and the gasoline. And then we can do the next step, right? That tells us how much of a car and how much of a tire we need. And then we just do the math. I'm feeling constrained by talking here. I can't point there and I can't point here. So let's just look at one. The steel, so you have 0.005 cars times 1,200 kilograms per car. The cars cancel out, times 2/3 were steel, so that ends up 4 kilograms of steel. And of course, you have to make the steel, and that goes up. So anyhow, so that's the next step, is trying to put numbers on our inventory. We're not ready to do that yet. We're gonna get you started on the life cycle thinking. What is everything involved with this? Now, of course, this is a very incomplete, right? It was a simple example to show you the type of math that's done. But this just tells us sort of the bill of materials and what goes where. You still have to do a lot more calculations. So one calculation we can do, we know that we're using 80 liters of gasoline. What is a primary emission that comes out of gasoline consumption? NOx is an important one. Anything else? Carbon dioxide is the biggest one, right? That's what we want. If we had perfect combustion, all the carbon in the gasoline would come out as carbon dioxide, right? That's what we want. But we know carbon dioxide's not good. So how do you come up with how much carbon dioxide comes out of a gasoline that out of a automobile that consumes 80 liters? So this is just one example. We often have what we call emission factors, and these are things that you can look up. And so the emission factor is just, it tells you, so in this case, if you combust gasoline, that's our activity, times some emission factor, you get the total emissions. And we're gonna combust 80 liters of, that should have said gasoline, for 1,000 kilometers driven. So you have to go look up emission factors. I'm familiar with the ones that I find in the United States, so this comes from the EPA. Now that's our emission factor, 2.5 kilograms of carbon dioxide per liter of gasoline combusted. And so we just multiply that by 80, and now we have an output, 200 kilograms of carbon dioxide for this functional unit of driving 1,000 kilometers. So in gasoline, in reality, it doesn't really matter where you combust it. 99+% of the carbon in the carbon dioxide, in the gasoline, ends up as carbon dioxide. And that's why you can use US numbers for things like combustion. It's no different. It doesn't matter what vehicle you put it in if it's per gallon combusted. If it's per automobile, then every automobile is different because you have different fuel economy. But if you've got an emission factor per gallon, a gallon of gasoline is generally a gallon of gasoline, regardless of where you are. So now you can add that. And there's emission factors for NOx and all sorts of other things as well. I just wanted to show you that. So what did I need to do this example? I needed to know something about a car and the basic materials in a vehicle. I needed to know something about operation of the vehicle, the fuel economy, the rotation of tires and headlights, the basic materials that they're made up of. and then some emission factors. So that's a really easy example to show you the kinds of things and the calculations you can do to start filling in some of the mass and energy flows and some of the early emissions. And then there's software to help us, which we're going to just play around with a little bit, but I just wanted to share that with you. So the other upstream, like how you make the steel, how you make the polypropylene, you often go to a database that has all that upstream. You look up steel, it gives you all the life cycle inventory output for steel, or come on in, for something like that. So I just wanted to share that with you to give you some idea of life cycle inventory types of calculations. But using the software, using process flow modeling, engineering modeling is also a big and important part of creating the life cycle inventory, the input to the inventory. And then some software would help you with the output of that software. Still the life cycle inventory. All right, so I am gonna skip this one. And I did that pretty quickly. So are there any questions on any of that? That was a classic undergraduate textbook example, right? Really simple. But my goal, and Bindu helped me find this, was to help you understand just a little bit of the process. Nothing is going to be as simple as that, but it helps you to get started when you think about the things that you need to know, right? The composition of the material, everything that goes in, how those things were made, what might be creating the biggest emissions, will help us understand that for a very simple example.